In this video, we review how to solve systems of linear equations using substitution, elimination, and we'll even practice some graphing. Let's get started. So recall that if you have a system of linear equations, we're talking about equations whose highest power or degree is 1. Meaning, these equations, as long as there's only an x and a y, no third variable z, we'll get to that eventually, these represent what we call lines. Linear equations with two variables x and y always represent lines. So if you have two or more lines in a system of equations, to solve that system would really be answering the question, do these lines ever intersect or equal each other? If they do, please find out where. That's what it's asking you. Very practical application. If you're talking about a business and you have cost and you have revenue, you need to know when your cost and your revenue are going to intersect. If they're parallel and they never intersect, that's not a good business, right? If they are on top of each other and your cost and your revenue are always the same, that's also not a good business because then you're always just breaking even and you're actually not making a profit. So we prefer the situation, most students prefer the situation where your lines are crossing each other at exactly one place. So let's talk about what that looks like in our little picture here. In the first picture on the left side of the screen, it talks about a system which is what we call consistent. A consistent system, feel free to write this in your notes, a consistent system is a system of equations which does in fact have a solution. Now it might just have one solution. When the two lines cross in exactly one location, like in this picture, there's one independent solution. On the other hand, if you look at the third picture in the frame, on the right side of the screen, technically the red and the blue line are intersecting everywhere. That's still going to be a consistent system, but it's a consistent dependent system. Whereas the first one was a consistent independent system. Can't think I spelled that wrong, but dependent. You can look that one up. All right. In the middle, however, you have a situation where, as I mentioned with the business model, the two lines are never intersecting, and that's because they have the same rate of change, and they started at different intercepts, at different y-intercepts. So they have different y-intercepts, but they have the same slope, rise over run, right? 3 over 2 or 1 over 2, something like this is happening. So if lines have the same slope, but they had different starting points, different intercepts, y-intercepts, we would be talking about parallel lines, and parallel lines can never intersect, which means if you wanted the solution to a system of parallel lines, you would say there is no solution. Sometimes you'll write that as the empty set, right? Or some of you prefer a circle with a line through it. They both mean the same thing. There is no solution for that system. So if you were graphing the systems of equations, you could easily tell whether or not you are in one of these three situations. Are the lines on top of each other? Okay, a consistent dependent solution. Are the lines parallel but never touching? Okay, an inconsistent system with no solution. Or finally, are the lines touching in exactly one spot? Yes, that would be a consistent independent solution. So graphically speaking, if you have graph paper and a ruler, you can answer these questions all day long. You might be approximating the solution based on the graph and the numbers, but you could at least get an idea of what's going on. It's better, though, for your future algebra proficiency that you know how to graph a system algebraically, which means without using the graph necessarily, by just solving using a method called substitution or elimination. These two approaches are what we mean by analytically or algebraically. So when they ask you to solve it algebraically, that usually means without graphing it. Okay, so let's take a look at those two methods side by side, and at the end, you're going to get to pick which method you prefer depending on what the problem looks like. Let's take a look. The first method I want to look at for our algebraic approach to solving these systems of linear equations would be substitution. Now, the good news is that these processes or algorithms that we're going to talk about today will work not only for systems of linear equations, but also systems of nonlinear equations, which you'll see in the next section, in the next video. So it is really fundamental that you know how to do these processes, these algorithms. So as the name suggests, substitution means we would like to substitute one variable with some other expression. Well, how are we going to do that? The first thing we're going to do is isolate one of the variables. So we start by solving one of the equations for one of the variables, either x or y. You get to pick. Now, if they already have given you one of the equations where y is by itself or x is by itself, it's already begging to be substituted in for that variable in the other equation. And that's where we are at step 2. Step 2 says substitute the result found from step 1 into the other equation. So if you found, for example, that x equals 2y plus 4, you would go to the other equation, and anywhere you see an x, you would write parentheses 2y plus 4. That's the idea. Once you've done that substitution, what you've really done is you've gone from a system of 2 equations with 2 unknown variables to a single 1 equation with 1 variable, in that case y. So that would be where you could solve that linear equation for that variable. That's step 3. Solve the equation found in step 2 to find the value of one variable. Now, once you have one variable, you back substitute it into the other equation, or the equation you're working with, to find out the other variable. So we're substituting a couple of times. And finally, step 5. Once you've found your answer for x and your answer for y, make sure it works, because there's a chance that you made a mistake, right? We are human. So there is a chance that you found the wrong value just because of an arithmetic error. So always, always, always check if your input and your output, if your x and your y really do satisfy both equations. If it only satisfies one but not the other, you do not have the correct point, because a point that is a solution to a system is a point on both lines. So let's take a look at a real-life example from economics. Anytime you're talking about economics and there's something being sold, maybe it's an iPhone, whatever it is, that has a certain demand and a certain supply depending on who is producing it, right? So let's say a particular business has a new device and they're going to sell it, and they start off with a very, very high demand. They didn't realize it. They didn't think that many people would be interested. And so as you can see here, the red demand curve starts off at 100. People really want this item. 100 people, or in this case it's tickets, 100 tickets are wanted. And at this point, when they set the reason that 100 people want tickets, look at where they've set the price for those tickets. It's at 0, right? If you say I have a ticket for something and I'm not charging anything, sure, I'll take one, right? Most people would. And that's why the demand was super high. So they said, okay, we don't have that much supply, so we need to increase our ticket price so that we decrease our demand. So now they said, okay, what if we decided to charge, let's say, let me pick a number here that I can see. Let's say we charge $20 now, $20 per ticket. What they found was when they charged $20 per ticket, there were now 1,000 instead of, I'm looking at this correctly. Yes. Yeah, okay. So now we notice that it should be, if this is done correctly, as the price goes up, the demand should go down. And as you continue going along, they have to continue to figure out where the price should be. And this is usually what happens behind the scenes of businesses. They don't necessarily want to roll out their product until they already know what the demand for the product would be. But if they were starting from scratch, they would look at all of these data points and they would zoom in on the spot when supply and demand are at what we call equilibrium. At the equilibrium point, your supply and demand are the same. So you're not going to overproduce or oversupply your items, but you're also not going to undersupply those items. So they found that in this case, according to the model here, when 2,000 tickets are demanded, they had set the price at $40. Okay, so again, sometimes it's a negative relationship, other times it's a positive relationship, depending on the type of thing you're selling. So let's take a look at the equation that models supply in this case. It looks like supply was given by y equals 0.02x. Where did those numbers come from? Well, m is your slope, right? We remember that for equations of lines, in slope-intercept form, y equals mx plus b. M, the coefficient of x, is your slope or your rate of change. So you go up by 0.02 and over by 1. And that's what's happening here, going up by 0.02, over by 1. The numbers here are just a lot bigger, so that's why at the 0.02, when it multiplies out, it makes more sense. Okay, notice also that our y-intercept looks like 0 here, because originally the supply was at 0. They had nothing available. All right, so then we notice that the demand, on the other hand, has a negative slope. So the demand is going down, it looks like, as the demand is going down as the price is going up, it appears. So we have, in this case, negative 0.03x plus 100. The y-intercept here is a little bit different. It's starting out at a demand of 100 in this case, even though the supply starts at 0. So that's why they're starting in different spots. All right, so once we have this set up, we have the two equations, and we'd like to know when supply and demand would intersect. It's called the equilibrium point in this example. We could use the substitution approach. Step 1 of substitution was to isolate one of the variables. Well, we already have that done for us in the first equation, don't we? Y is by itself. So I could substitute the expression that y equals for supply, which is 0.02x, for what y equals in the demand function. So I'm going to do that. I'm going to take 0.02x and substitute it for y. In other words, I'm simply setting my supply and my demand equal to each other, and I'm trying to see if this is possible. So when I do that, I get 0.02x equals negative 0.03x plus 100. So now we have a linear equation. We went from two linear equations with two variables x and y to a single one linear equation with just one variable x. And you could have solved for either variable, but y was already by itself, wasn't it? So now we've done steps 1 and 2. We're on step 3, where we need to solve for this variable. So how do you solve a linear equation for x? That's right, just get x by itself on one side. So if this were me, I would probably try to get all of my x values to be positive. So I would add 0.03x to both sides. 0.02 plus 0.03 is 0.05. So now I have on the left side 0.05x and on the right side 100. Now, if you could do this particular problem in your head a lot faster, you don't have to write all these steps out. I'm not trying to slow anyone down, but I want to show you the step-by-step way of doing this because when we get to more complicated problems, if you understand the process of, or the algorithm of substitution, you're going to be able to smoothly sail through that problem. So let's take a look at how to finish this one off. We would simply divide by whatever's touching x, right? And if you divide 100 by 0.05, what do you get? You get 2,000, right? So in this case, we get our answer of 2,000, where 2,000 is our x. Now, what did x represent? What was the x-axis? X was the number of tickets, right? So we now know that when there is a demand and a supply of exactly 2,000 tickets, that's when we will be at our equilibrium point, okay? But now the question is, well, when would I be at a demand and a supply at the same time of 2,000 tickets? Well, I could now go to we did step 3, I can now go to step number 4, where I need to substitute that answer into one of the equations to solve for the other variable. So let's head over to step 4 now, right here. So to do step 4, I could either plug x into the supply function as x, 2,000, or into the demand function, because we're claiming that they're the same at this location. So I'm going to pick the easy one. I'm going to pick the supply function. And if I go into the supply function, which said that y should always equal, my output should always equal 0.02 times x, where x is the value we just solved for by substitution, which was 2,000. If I multiply that out and I do 2,000 times 0.02, shouldn't I get 40? And what is y supposed to be? If you look at your graph that was given to you, y was your price. So when I set each ticket at a price of $40, so $40 per ticket, then I can expect to have a demand of 2,000 tickets. So 2,000 people will want to buy my tickets, but I also can supply that many without having to be in debt or anything like that. It's a perfect place to be, where my exact supply and the demand for my item are identical. So that's the sweet spot when you're running a business or when you're looking at an economics context. When demand and supply intersect our equilibrium point, that is where things are very, very nice for our model. Okay, so what did we do one more time? We used the substitution method because one of the variables was already isolated. In fact, y was isolated in both equations. Once you saw that, you just plugged in that expression into the other equation. In other words, you set them equal and solved. Now, I mentioned the importance of step 5 checking, but I didn't actually demonstrate the check. To check this, we already showed that it worked in the first equation, right? 0.02 times 2,000, which was x, gives you your y value of 40. But it better work for the second equation as well. If you type in negative 0.03 times x, which is 2,000, and add 100 to it, you better get an answer of 40. If you don't, then we did something wrong. So go ahead and check that and know that you're right. Once you're there, we'll head to our next slide. The next slide gives you an example to practice. So go ahead and pause the video and try to solve this system of linear equations by substitution. The system is 2x plus 1y equals 9 as your first line, and y equals x minus 3 as your second line. Notice that they're both linear, degree 1. In our next video, we'll see parabolas and circles and all kinds of other equations, but right now, notice they're both linear. So take a moment and see if you can go ahead and answer the question, where do these lines intersect, if anywhere, and then maybe even graph it if you have time. So what I noticed, if I was solving by substitution, I think I mentioned originally in the notes here, I'll probably delete these after the video, but it said substitution or elimination. Technically, you could have done elimination, but since we haven't talked about it yet, let's stick to our plan. Let's try substitution. So for substitution here, I would look for a variable that's already been isolated. This one has y by itself in the second line, second equation. So that would mean I could substitute for y in equation 1 by replacing it with x minus 3. So this is my substitution step. I would have a new equation 1. It would be 2 times x plus whatever y should equal, equaling 9. When I replace y with x minus 3 from equation 2, I now have an equation of 2x plus x minus 3 in parentheses equals 9. Now the reason I use those parentheses is because if there was something in front of y, I would need to distribute it to everything in the parentheses. That's why it's good form to put the parentheses in case there is a distribution needed. But here, since this is just a 1, there's really no need. You would have 2x plus 1x, which is how many x? 3x, good. And then you'd have 1 times negative 3, which is negative 3, equals 9. You didn't have to show that distribution because it was just multiplying by 1, which doesn't change anything. To solve for x now, you can add 3 to both sides. Make sure you go right order of operations. So 3x should equal 9 plus 3, or 12. You can now divide both sides by whatever's touching x, which is 3. 12 divided by 3 is 4. So you now should have that these two lines do intersect somewhere. Our solution set would consist of a single point when x is 4. But we're not done. We need to know the y location, the output, when these are going to be the same. And so to find the output, what did we do next after you found the input x? That's right, you substituted into one of the other two linear equations. Now right now, when they're both lines, it doesn't matter which one you substituted into. When we get to higher level functions like parabolas and circles, you will always pick the one with the lower power. Okay, so since they're both power of 1, no difference. So I could plug x in right there in the second equation. That would probably be the easiest. And I would get that y should equal 4 minus 3, because x here we found a moment ago was just 4. And 4 minus 3 gives us our answer of, that's right, 1. So we now have that y should equal 1 when x equals 4. So the input of 4 gives you the output of 1. All right, so we have our solution set. Now before we declare our victory, let's see if it makes any sense on our graph. You can either do it by hand or check Desmos, but since most of us need practice graphing lines, let's go through the process. To graph the first line, for example, line 1, it was originally in the form 2x plus y equaled 9, right? So what I could do is I could get y by itself, or I could use the intercept method. I'm going to get y by itself. So I'm going to say line 1 is technically the same thing as y by itself, and I'm moving 2x to the other side, negative 2x plus 9. So if I put 9 as my y-intercept, 1, 2, 3, 4, 5, 6, 7, 8, 9, there he is at 9, and then travel down 2 and right 1, because negative 2 is really negative 2 over 1. So down 2 lands me at 7, so 1, 2, and then right 1, and I could keep doing that. Down 2, right 1, down 2, right 1. You see the idea? Down 2, right 1, down 2. You can get the idea. Okay. Now we're claiming that at 4 we should be at 1. And is that what happened according to my slope here? Yeah, here is 4, comma, 1, right there. So that point is in fact on that line. So that's at least good news. If it wasn't on the line, we'd have a problem. So let's see if I can draw that line without going a little loopy here. I think it went through. Okay. So there is line 1 with a key point of intersection we're claiming at 4, comma, 1, our solution. We call this solution, by the way, when you go into pre-calculus one day, a point of intersection, or a POI, right? So that's going to be important when you have multiple graphs intersecting. You need all the points of intersection. All right, well, let's try to find the second graph to see how this makes sense. For the second graph, let me pick a color you might be able to see. I'll do purple. Line 2. This one already had y by itself. Y equaled x minus 3. So I could start at a y-intercept of negative 3, if we remember how to graph lines. So there's negative 3, my y-intercept, and a slope of 1, which means go up 1 and right 1. We'll keep doing that. Up 1, right 1, up 1, right 1, up 1, right 1. If you had a ruler, this would be faster. Up 1, right 1. Hey, there you go. We just intersected at 4, 1, didn't we? So this does in fact make sense. We stumbled upon, both graphically and by substitution, the point of intersection, called the solution of this consistent system. So when we go on to inequalities, we'll add shading as one more component to this graph. But finding this point of intersection will be a critical part of solving a system of equations and systems of inequalities. All right, so if you didn't follow that one very carefully, go ahead and go back and try it again until you feel very comfortable with substitution and graphing a system showing the solution. Now I'm going to head on to my next slide. If you're ready to come with me, feel free. The next slide is talking about the second approach to solve systems of linear equations algebraically. It's called the elimination method. However, some textbooks would refer to it as the addition or the elimination method. So if you hear one but not the other, depending which math class you go to next, just be aware they're the same thing. In a moment, hopefully you'll understand why both names sort of make sense. So the key distinction between substitution and the elimination or addition method are that substitution requires the person to first isolate one of the variables. Now, if you notice the system in the example on this screen, we only have one variable which looks easy to isolate, and that looks like y in equation 1. So if I was trying to solve that system by substitution, I would most likely get y by itself in equation 1 by scooting 2x over to the other side using subtraction, right? However, if I don't want to do that, another option is to simply line up the variables like they already are. So line up the variables. So the x variables on top of each other, the y variables on top of each other. Notice because they're linear, these would be like variables. When you get to nonlinear equations, where you might have a circle and a parabola, it's really important to only recognize true like variables. Like an x and an x squared would not be like variables, would they? Okay. So once you've lined up like variables, the next thing you want to do is to think through what would happen right now if I added my variables together, which are the same. For example, if I added my 2x and my 5x, what would I get in this example? 7x, right? The purpose of adding here, the addition method, right, is to eliminate one of the variables. So right now, does 2x and 5x, do they get eliminated if you were to add them together? No. What about 1y and negative 4y? What happens if you were to add them together as they currently are? They would be the same. You would get something like negative 3y. That's not eliminated, right? So you might be thinking this method kind of seems strange. Nothing is happening. Well, you're right. We need to make a change. Now, it turns out, if you remember from our first slide today, there is a situation where a line can be on top of itself. It can be the same line but in disguise. That happens if you've multiplied an equation of a line by a constant number, like if you double everything or you triple everything. It turns out that it's the same line. Really? Yes, because what you do to one side of the equation, you must do to the other. And if you've done the same thing to both sides, you could undo that by dividing. So it means the same thing. So if I wanted to make a change so that when I add these two variables, let's say the y variables, so that they would cancel, what would I need to have in equation 1? So that when I add the y variables, they would cancel, let's say. You would need a positive 4y, wouldn't you? If you had a positive 4y, that would eliminate the y variables, wouldn't it? So how could I make positive 1y turn into positive 4y legally? I would have to multiply every single term in that equation by what number? By 4. And so that's what we see in steps 2 and 3 eventually. In step 2, we determine what we need to be there. We need it to be a 4y so that the y terms would eliminate. Now you might be wondering, why didn't I go after the x terms? Well, notice that 2 and 5 don't really have anything in common. So you could make one of them 10x and the other one negative 10x because that's their least common multiple when you multiply 2 and 5 together. But that takes more multiplying, right? You have to change both equations, and you'd want to make one of them negative, one of them positive, and so that takes a lot more forethought and work. So if you notice that one's already positive and the other's already negative, and that it's pretty easy to make them cancel, then you go with that one. And so that's what I've done. I decided I will now make the coefficients opposites by multiplying equation 1 by 4. So let's do that. Let's multiply equation 1 by 4. As long as we do it to both sides, it's perfectly legal. So the new equation 1 becomes 4 times 2 is 8, so 8x. 4 times 1 is 4, so 4y. And 4 times 7 is 28. Now look what I have. I can copy and paste my equation 2 here. It didn't need to change. 5x minus 4y equals negative 2. there's my new system. Technically means the same thing because when you multiply both sides of equations by any constant, as long as it's not 0, you haven't changed anything. Now look what happens when I add my terms together. Now we're on step 3 of this algorithm. 4y minus 4y dies. Death to you, death to you. What's remaining? Well, 8x plus 5x. That's just 13 copies of x. And 28 minus 2, the constants, that's just what? 26. Notice here a mistake that students typically make is they forget to multiply both sides of equation 1 by the number 4. If you did not multiply that 7 by 4, this would not have worked out correctly. You have to do it to both sides to actually be legal. Dividing both sides by whatever is touching x, you'll get x equals 26 divided by 13, which is a nice number this time. Sometimes there'll be fractions, that's okay. But in this case, it's just the whole number 2. Now we found one of the two answers for the solution set. We found the x value of the ordered pair. It's 2 for x, and we need to find the y value. How did we find the y value, you think? Yeah, we can plug it in, exactly. So we're going to now, we've solved the system, we've done that, but now we're going to substitute that result into one of the original equations to solve. I would probably plug it into the first equation for x, because that's the easiest way to get y by itself, it looks like. So this would become 2 times my x plus y equals 7. We're doing step 5 right now. My x that I just got was the number 2. So I inserted my x that I just solved for. 2 times 2 is 4. So I have 4 plus y should equal 7. So what should y be? That's right, 7 minus 4, or 3. So when x equals 2, y should equal 4. This should be my solution, and you could check by graphing. There's a Desmos link in the notes provided to see if the ordered pair 2, 4 is in fact the point of intersection for these two lines. Also, you could check by plugging them back in. Does 2 times, we already did this one, but does 2 times 2, which is 4, plus 4, did I say that right? Yes, 2 plus 2, which is 4. I wrote it wrong. This is a really good check. I'm glad we did this. It should have been a 3 there. My goodness, did you catch my error? I hope you did. Does 2 times 2 give you 4, and 4 plus 3 give you 7? Yes. That's how I caught myself. I had miscopied the number. I wish I could say I did that on purpose, but now you can see how to catch your errors. Check the second one for me. 5 times x. So 5 times 2 is 10. 10 minus 4 copies of 3, well, that's 10 minus 12. Does that give you negative 2? It does. And now you know that you are 100% correct. You found the only solution to this system of linear equations. This, again, would be called a point of intersection in your graph. All right, let's see if you can apply this method to the next example on your own. Feel free to pause the video and give it a shot. It says solve the system. Technically, it gives you both options, but I'd like you to try the elimination approach. X minus 4y equals 16, and 2y minus x equals 2. So give it a shot and come back and see how you did. Okay, if I was doing elimination on this one, first thing I need to notice, and it's easy to miss, is that my variables have to be lined up. Typically, we go in alphabetical order. So line 1 is x minus 4y equaling 16. And line 2, if you rewrote the order, is negative x in front and positive 2y second equaling 2. Well, it turns out that makes our life really nice, doesn't it? Did you see that? Because when you add these variables together, what happens to your x values? That's right, they cancel because they have opposite but the same otherwise numbers here. So this is positive 1x, negative 1x. When you add those together, they wipe each other out. That's 0. So now all that's left is negative 4y plus 2y, which is in fact negative 2y, and 16 plus 2, which is in fact 18. So when you divided by negative 2 to get y by itself, you should have gotten y equals what? Negative 9. Yep. Okay, now that you have a potential answer in your solution set here that y should be negative 9, how would you go about finding the x value for your solution or your point of intersection? Good, you plugged it back in. Now remember, since they're both same degrees, both lines, it doesn't matter which one you plug them into. When they are different degrees, you'll always plug them into the lower degree. And that'll make more sense as we get into it in the next video. So I'm going to plug in my y value, let's say the first equation. You could have done either one. If you plugged it into the first equation, I get x minus 4 copies of y, I use parentheses for the unknown, equals 16. And y we've just found to be negative 9. So if I multiply a -9 by a -4, I get a positive, watch your signs there, 36 next to x, equaling 16 on the right. Solving for x, watch your arithmetic. X should equal what number? 16 minus 36, isn't that -20? So now you have the potential solution of -20, comma, -9. Now how do you know you're right besides clicking on the Desmos link in your notes? That's right, you plug back in. So if you did a quick check, I'll just show you one more time how you could do a quick check here. If you wanted to do a quick check, you would simply say for the first equation, so line 1, what do I get? I would get x, which is -20, minus 4 copies of y, which was -9. Does that equal 16? And we just did that one a moment ago. That was in fact -20 plus 36, which does give you 16. For line number 2, on the other hand, I need to take 2 copies of y, which is -9. I need to subtract x, which is -20, so watch the double negative there. And the question is, does that give me 2? Let's see what happens. You get 18, -18 I should say, -18 plus 20. That is 2. So you have practically checked, you've exactly checked, that the same point exists on both lines, which means that this is your point of intersection. So this is a consistent, independent system. All right, so at this point, we have now demonstrated and practiced together substitution, elimination, and we've checked even with graphing, to solve systems of linear equations. In our next video, we will be solving systems of non-linear equations. So before you can even attempt to meet me there, you need to become a master of these 2 skills. So make sure you practice, because math is not a spectator sport. I'll see you next time.